If you are watching this video, I'm guessing you are also a TCD student currently taking Mathematics of Light and Sound. It's my favorite course this semester, but the code for the wave simulation is honestly painful to read. So I decided to kill this pain for you. If you are struggling with the code or haven't even started yet because you have been too busy, I have refactored and packaged the code to help you out. And I can guarantee my code, it works on your personal computer. First, pip install Wave Simulator. Yes, it is just that simple. Of course, you can also get the source code from my GitHub. Second step, import this package and define your initial conditions, such as the initial waveform, boundary conditions, and wave speed. Third step, start the simulation and display the result. I have provided some simple examples that should make it clear how to use it. To set the initial waveform, you can define a function that takes the coordinates as input and returns the initial waveform value at that coordinate. Initial particle velocity is set up the same way as the initial waveform, except it returns the initial velocity of the particle. Note that the initial particle velocity refers to the vertical speed of the specific point at the initial moment. Don't confuse it with the wave speed. For instance, if you initialize a sine wave but don't set an initial velocity, it will only oscillate in place, or perhaps gradually dissipate depending on your chosen boundary condition. But if you want it to move left or right, you need to give its particles an initial velocity. You can also define the medium's wave speed in the same way, allowing you to observe refraction and reflection between different mediums. I have defined 3 types of boundary conditions here. The first is a fixed boundary, just like one end of string that is fixed at a point. The second is Newman boundary, where the slope at the boundary is constrained to 0, like the end of a string tied to a ring that can slide freely on a rod. The third is unlimited boundary, which simulates an infinite boundary. You can set different conditions for different boundaries like this. For more API details, you can refer to the documentation on my GitHub. Next, I will briefly explain the general implementation principle of this simulation code. Open the source code and you will find 4 files. Animation utils handles the logic for displaying animations and saving videos. It's not critical. Boundary conditions contains the implementation of the boundary conditions. 1D simulator and 2D simulator are the 1D and 2D simulators respectively. Let's take the 1D for example. The one-dimension simulator class will have some initial values during initialization, which you can modify before the simulation begins. Let's just jump right into the core simulate function. Result is used to store the simulation output. uLast, uCurrent, and uNext store the waveform at the time steps I1, I, and I+1, used for the iteration calculation. We will fill uLast with the initial waveform. However, based on the finite difference form of the wave equation, we need waveform data from at least 2 time steps to calculate the next step. Therefore, we also need to get uCurrent. Here, we use the initial velocity of each point and the acceleration to estimate uCurrent. You might notice a lot of array slicing in this part of the code, which can be confusing. This is because directly iterating through the array and operating on each element would be very slow. That's just how Python is. The slicing here essentially means that if 1 to n is taken as I, then 0 to n sub 1 corresponds to I sub 1, and 2 to n plus 1 corresponds to I plus 1. The variable names are very straightforward, but if you are still confused, you can check the documentation where I will provide the corresponding mathematical expression for each variable. You may have noticed that after the slicing, we only calculate the result of the middle of the array. The 2 endpoints haven't been calculated because they don't have the left or right element. So the next step is to apply our boundary conditions to calculate the 2 endpoints. I'll explain boundary conditions later. After obtaining uCurrent, we can officially start the iteration. You can see that in this loop, we first calculate the middle part of uNext using the finite difference form of the wave equation, which is represented by u next I. Then we apply the boundary conditions to calculate the two endpoints of u next. Finally, we store the result in the result variable and shift our u current and u next to become u last and u current. By repeating this process, we get the simulation result. Now, let's look at the boundary conditions. First, I defined an abstract class boundary condition to define the two interfaces, one for 1D simulation and one for 2D simulation. The 1D simulation has left and right boundaries, and the 2D simulations has additional top and bottom boundaries. But using symmetry, we only need to implement one direction. Here, we will take the left boundary as an example. Fixed boundary is the simplest. It just returns 0. Under this boundary condition, the wave will reflect and undergo a 180-degree phase change. Newman boundary. The principle is to constrain the first derivative at the edge to 0. Under this boundary condition, the wave will also reflect but without a phase change. Unlimited boundary is calculated using the function for one-way propagation of waves. Note that this 2D implementation doesn't perfectly absorb the incident waves, especially when the angle of incidence is large. You can try to implementing a perfectly matched layer yourself for better results. Yes, this simulation code is far from perfect, but I hope it will be a better starting point. You can try to improve accuracy by using higher order approximations or implementing other boundary conditions on top of this. But please remember, this project is purely for learning. Please do not use it for serious applications, as I cannot guarantee that the code I rushed out in 2 days is error-free. Anyway, I hope this video helps you out. Thanks for watching.